Now it's time for product design. I'll be going through the major concept because product design itself is a vast topic. So, what is a good part? So, good part means it's a combination of the good part design or product design, then good tool design and good process molding and good proper selection of machine. So it is a combined effect. We cannot tell no if the part quality is lesser. We cannot point out to only one. It can be combined and or sometimes no major problem may come from the part design tool design. So I am a person who always insists on part design and tool design to take care of the maximum quality of the product. And processing side, if these both are taken care, maximum problems come from here only. Processing, if tool is qualified properly, part design is meant, looking all the then processing people don't have to put an extra pressure, and they don't have to do the processing window is very narrow. Whenever there is a narrow processing window, whenever my process molding is set so much critical to get a quality part, then that is going to deviate and rejection or failure is going to come. So as a designer, we have to know before making the part, we can do some more flow and whatever we can do and take out all the experience. And tool maker also should understand the gate freezing study, pressure drop study, free flow temperature drop studies, shear rise studies. So everything we have done, then it will be easy for the molding person to process the part. Very, very easy. We have seen this again. Everybody has seen this. Two molds we had done for the same part. One mold will easily run in anybody can set very easily. But other mold, only one person, with lot of struggle he can set. And we tell, you have done a good job. No, he has done a good job, but we have done a bad job. The designer has done, or the qualification, the tool maker has a bad job. That's why we are telling processor as molder has done a good job. No, it should not be dependent totally on the processor. When we move that mold to another place, we cannot replicate that. So very, very important to take care all these aspects at the time of design itself. Minimum things. I tell you 5% only we should be dependent on the molding person. And if a good tool, whatever tool I make sure that within 5 shots, okay part comes. If our part, if when we are molding a part and we are getting a good part after a 50 shot or 100 shot, that means design or our tool is not at all good. That is easy method to understand that. My part is coming in a 5th shot, 6th shot, my part is coming okay from the mold. It means I done a design fine, tooling I done a good job. That's all. So these are some designers know, and this is simple. Whenever we are designing, this is known as a surface of the part. Just point. Outer surface is known as A surface, and these are known as shut off. Wherever there is a through and through hole, it is known as shut off surface. You can see there are multiple elements like snap fits will be this requires some side action or a side core. The through and through holes with boss will be there. These are like mouse holes. Then air vending will be there to escape. If we are designing some product like UP or something, laptop, or there will be place for the hot air to escape outside. And multiple you can see all these things have been marked. Boss or gazettes are there, to support the boss we give gazettes. It is known as gazettes. So this is known as the nominal wall thickness of the part. Wall thickness, when we talk about wall thickness, plastic calls for a uniform wall thickness. Uniform wall thickness means cooling rate will be similar and drastic. If we have to change any wall thickness, section change, it has to be smooth. It's not suddenly step up. This is what it is shown here. Okay. See, thickness is so much difference. What happened? Cooling difference will come. One will cool and then it part may warp or sing mark will come. Second is okay, little bit better. The third is they are given a radius, smooth transition. Whenever plastic is there, even to stress not to accumulate, also we have discussed, there should be a smooth transition. Some radius should be provided so that uniform transition will happen.
Subhash, I have one question. So, as per your knowledge, so what should have to be the wall thickness minimum and maximum, nominal one?
You see, it is based on the raw material. No, if you are using a polycarbonate, it can be start from 2 to 5 mm. Some metal can go above that. If some metal you have to go above that, then you have to use some filler, like forming agent has to be used, so that it will not collapse. So it is like that.
So if it is you're taking a best material, so if I'm going, so what thickness I can go?
See, plastic
Increase
cannot
it.
be molded so much higher thickness because cooling internal area will not cool.
Okay.
So based on if it is much better conductivity, you can go for a slightly 6 mm, 7 mm, 8 mm. But then in the mold, you have to put that much amount of cooling line. Sometimes you have to put it into water to cool. It is like that.
Okay.
It's better to have thickness from 2 to 4 to 5 mm. That is the best for all the raw materials, not beyond that. Okay. But in some case, you have to go because higher pressure is getting built up. It is a pressure chamber. You have to go for 10 mm. Then based on that, you have to give cooling. Sometimes you have to go for a conformal cooling. Sometimes you have to put it in the water and take it and anneal it again to remove the stress. All these things has to be done. Okay. 2 mm, 2.5, 3 mm are good amount of well thickness.
So minimum?
Minimum, see, if it's a nylon, you can go to 0.6 also. PC, you can go to 1.7.
Nominal wall thickness, I'm asking. Nominal wall thickness. 0.6.
Nominal wall thickness in the nylon can be 0.6, 0.8 also. If you flow, that also depends on flow. If your part is so much bigger, you cannot use a smaller wall thickness.
Yes.
It is combined. It's not just raw material. Flow length is there. What are features are there? All are there. Normally, for a polygon, we tell 1.7 to 2 is a good thickness for a normal size of part. Like 50 mm. There is a testing for that. Okay, it is known as the spiral flow, and the biscuit we will be making at the lab scale. And every raw material, it is there in the data sheet, and you have to ask to the raw material up to what length, what thickness can be maintained. Okay, how much flow length this is possible. Looking at that spiral flow rate, there is a jalebi like thing will be made, specimen will be made. We'll be filling that. If that fills for a longer jalebi, it means it can go for a shorter, thinner part. Predictive analysis is always better. Instead of making the costly tool, lakhs of rupees and spending and rejecting that. So do some predictive. Do experience is not a predictive analysis is better. Whenever we are going, see, I told you, polycarbonate 1.7 mm thickness. If we go to a copolymer, you can fill in 1 mm. That's how cost saving is being done. Raw material cost will increase, but here the weight will reduce. Some raw material will fit inside same cost. Then your transportation cost will reduce, logistic packing cost will reduce, end product will cost will reduce because lower the weight. So this is how value engineering is being done. It's not a hard and fast rule. No, you ask this material, but no, because length changes, it changes. Thickness changes, it changes. Melt temperature, hot runner, it changes. Cold runner, it changes. So there is a thumb rule to understand, roughly, but you cannot tell all the part will behave the same way. So that has to be taken. So to give that indication, we have MFI. Already MFI is there in the data sheet. My material polycarbonate having 10 MFI. If I feel I have to reduce little bit thickness, 0.1, 0.2, go for a MFI of 18 mm, 18 MFI, or go for a 2022 MFI. This is how it has to be done. And how we get a understanding looking at data, there will be a supporting document showing that spiral flow, this material will flow this much. I will go to that. It comes in the last slide. And ejection. Ejection means draft angle. Amorphous material, we have to give for a higher draft because its shrinkage is less, it sticks to the cavity more. So cavity area more draft has to be. So draft is very important. Appearance, if we are giving some texture or something in appearance, what are texturing can be done. How much, if we are giving a texture in a vertical area, it has to be drafted. How much draft, extra, more the draft, better it is. It will be there in the even the when we are going for a texture, they themselves will recommend. Or every good product design company have their own studies and that also in that, because it depends on their product, not only just raw material. How detailing you are giving. Then radius we have been discussing. Every short corner should be blended as much as possible. Otherwise, the stress concentration happens in the corners or sharp edge and start cracking. Then we have seen ribs. Ribs are just like supporting element. If you have made a part just flat, it will bend. To have an extra support or mechanical property, we are giving rib so that it will not bend. It's like a what we can tell reinforcement thing. And if when we are designing a ribs, there are chance sigma comes on top. So how to attend that, we'll be covering it. Then gussets are also supporting structures. So what should be the dimension of the gusset so that there will not be sing marks or singing mark on the part. And when we are designing a boss, how much diameter inlet, internal diameter external should be there. So when is a self-tapping screw, or this gives for self-tapping screw or a metal insert also we give. So there are some calculation, some rules are there, so that sigma mark also will not get, will get a better strength also. Both will be there. And there are depression. It is like coring out. When we, some thickness, some area locally, we have to increase for the performance of the product or the application. Then we have somewhere scoop the raw material inside, so that we will maintain the uniform thickness, and strength also will not be compromised. And swingage and tolerance. Swingage and all will go, what tolerance. Swingage we know with raw material, amorphous and semi-crystalline. Then we have to go and see the data sheet and our experience also. This is an example. This is the thickness of the part we can see. See here thickness. First one, it is so thick. It takes a lot of time to cool. There should be optimum thickness. It's not be some thickness we are giving in. So we can take 2 mm, 2.5. These are normal. 3 mm, 4 mm. 2 to 4 mm is an ideal thickness of plastic part. If we are making a small part, we cannot go for a 4 mm. So based on that, we have to design. And if it's a small part, then we can reduce the thickness because it easily flows and fill. Okay, and proper draft has to be maintained. Uniform wall we discussed. No, see this case. First case uniform but so much thick. Second case is uniform. Third case it's not uniform. Then one area will cool, other area there will be defect. So uniform wall thickness has to be maintained. That's what it indicates. Okay, here it is maintained properly. Radius is there, everything is there. See, this is a part designed for the function. It should look like this. This is thickness. So there is a thickness. We need that thickness difference. I don't have an option to reduce this thickness to make it uniform. Then what I will do? I'll do provide some ribs like this, or I can provide a ribs like this. So whenever we are providing rib, there is a proportionate. There is a rate that rib thickness. Okay, here I given a bigger thickness. Ideally, it should be like this. If this is a nominal wall thickness, base thickness, then the rib thickness should be 0.5 to 0.75 only. Otherwise, a big sigma mark can come in this area because this takes time to cool. Now see, load is coming in this direction, so these ribs will not help that load. That's why this rib will help better. So this is how we can use our logic. This is logic also. This will take more load in this direction. So that's why this has been designed like this. So both the case we can design both. What is the difference? Both are ribs, but yes, load carrying capacity will be totally different. This is a better load carry. Now you see there is a boss which is attached to the wall. My purpose is to just put a screw or whatever hole required. But if we are attaching this area, wall thickness is drastically going to increase, and outer area of the part you can see a sink mark. To avoid that, you have to give excess holding time. Our cycle time low, overpacking, our tool will damage quickly, our part will overstress. In molder stress will be more. Yesterday we discussed. So to avoid that, what we'll do? Okay, we should have this pole to have an assembly purpose. How to control that? Move it little bit inside. So wall thickness meaning give a gasket or attaching element to strengthen that. Now this is a part. Everywhere it is sharp corners. Stress will occur. So I have to produce a radius so that uniform wall is sharp corners avoid. It's simple, pretty simple. This is also like see. Now here there is no draft. Removal will be difficult. It may cavity catch to the cavity side. It may, if it is catching, and ejection also higher amount of pressure is required, then induced molder stress will be there. So what to do? Give a draft. Give a generous draft wherever possible. Don't tell half a degree my product design. All this product design team will tell half degree only possible. Because why? Because major reason they don't have to take a risk. But manufacturing is a total risk. Product cost is just giving a 1 degree draft, reduce the cost of the product like anything. Because he can, instead of 10 second, 15 second cooling time, he can operate in 7 second of cycle time. It can be easily pushed out. It will not deform. Otherwise, it keep cool the part more than its HGT, heat distortion temperature to eject, because and ejection pressure also more. Ejection pressure more means more electricity is consumed by the molding machine. So generous draft is always advisable. There is no limit to give the draft. Give whatever is possible. Give 2 degree, 3 degree is possible. Give it. Don't restrict quarter degree, half degree, and all this wherever it is possible. some area it may, it may call for a function, then okay, some area leave it lesser draft. Don't leave any part without draft. So now in the same case, if boss is the unsupported one. So unsupported loading problem. If you load, it can bottom side can crack, all these things. So give a rib. This is very simple. And everywhere he has given a round radius. And the rib thickness you see compared to base, it is lesser. That is very, very important. Or it can be designed like this. Gusset can be designed like this also. Instead of giving a lengthier one, if we are giving that lengthier one in a semi-crystalline, it tends to little more shrink more. So to avoid that, we can give a gusset like this. Or if an application calls for that area has to be left alone. We need some space, then can be designed like this. These are these just I will go through. See, if everything is derived on the nominal wall, this is the nominal wall thickness T, then the thickness of ribs, you can see T by 2 or T by 2 means 0.5. It can go up to 0.5 to 0.75. Height should be 4T. Okay, this can be 2T. Radius, outer radius means 1.5 times the T. If it is 1 mm is a wall thickness, then 1.5 will be the 2 mm, then it will be 3 mm. And inside will be like T by 2, thickness by 2. It is a 3 mm, then inside will be 1. So that uniform, only the logic is uniform wall thickness is maintained everywhere. That's all. We are giving 2 holes, normally you have to keep more than 2 times the thickness. Otherwise, filling problem, crack can happen. That's why. And whenever we are giving any gasket boss, radius has to be given at least T by 4. It's a if you give a big radius, then bottom side sing mark will come. That's why it is called T by 4. 2 mm part, then 0.5 is the radius. So we have to connecting ribs. So all these are same thing. Some distance has to be managed. Should not be so much clear. Near. Okay. See, now is the question. What should be the internal radius? Who can answer?
Half of the wall thickness.
Pardon?
Half of the wall thickness.
Okay. Right.
2 mm.
Yes. It is the
Wall
2
thickness
mm.
is 2, so it's
Then outside?
It too.
1.5. Okay. Then only that this see, if we give it here half and 1.5 here, then this distance will be same 2 mm. That's what we have to see. Uniform wall thickness. What is the boss? Below the boss, how much radius we should give?
T by 4, that is 0.5.
Yes, correct. If it is more, what will be the problem? If we are giving more, higher, some people tell.
Possibility of sink marks.
Absolutely correct. Absolutely. This is what we are already explained. 2 to 2.5 thickness. Everything should be related to thickness. That it will be better. Otherwise, we will struggle. Something has to be base, So we have to take the thickness as the base, and that thickness has to be maintained most of the area same wall thickness. Then give a draft half degree, 1 degree generous draft. Then distance, this is a rib. Distance should be 2.5 times the T, and this bottom area should be 0.5 to 0.75 T. If it is more, then sing mark come in this area. If it is more means, I'll show you what will happen. I'll exit the presentation.
It also depends on the material, right? It is not exactly we can't give 3/4 of the T, right?
What you are telling the thickness?
The rib width at the bottom, you can't give exactly off for 3/4 times of the T sometimes.
So now
it depends on the material.
Yeah, we are giving a tolerance. You already receive a band. Here 0.5 to 0.75 T. That is good enough to for all the material. Why it is so?
For all the material.
Yes.
All the material.
All the material. I'll just end the show. I'll show you why. Now I will show you what is the difference. When we inscribe a circle in this area, this material will take time to freeze. If you increase this, my rib is I am going to increase like this, exaggerating. The circle that get inscribed in this one, this will increase, right? Then what happened? This take extra time, more this thickness to cool. What is the result? Sing mark.
Sink mark.
Sing mark comes in this area sigma will come. That's why we are telling we have to maintain this. Whatever may the raw material, this has to be maintained. Okay, there is no resistance. Raw material has the same property, heats and cool. Every plastic heats and cool, whatever you can see.
Yeah. Subhash, this height of the rib,
Okay,
that we can have a minimal of
that can reduce.
minimum then,
Yes,
yeah,
minimum we can reduce,
based on the
no problem.
application of the.
Yes, yes. But maximum it is better to do 3 times, then filling will be proper. If you increase so much, one filling issue, then ejection issue,
Yeah.
I think all these things come, and even machining also difficult. When we go so much deep, when we are doing a sparking operation, what happens? There will be a chance of arcing. The cost of the tool also will go up. Okay.
And secondly, Suhas, I think that the ribs should also have radius on top.
Yes.
Possibly you have
Yes.
not given the radius.
Better, yes, sir. Yes, radius should be there. If this is a schematic diagram, I just want to show the dimension. That's why.
Okay. Sorry.
Okay. Yes, radius is mandatory if you want a good part. If you are making a part without a radius and with the radius, if you take a load of 10 kg with the radius, with radius take 100 kg, not even 20 or 30 kg. It can take 100 kg. That much drastic difference. Yesterday we have seen that loading capacity of a stressed part and non-stressed part. So radius is one of the important contributor. Even for flow also, for loading also, everything crack. And in this area, we were telling notch sensitivity. We have seen the notch impact strength of the polymer in the data sheet. This is sharp corners tend to notch. The notch, unnotch impact strength and notch we have seen. Unnotch was 3,500 and notch was just 600. That shows the difference in the performance. So don't give a chance for notch to form. Notch forms in the sharp corners everywhere. So don't make sharp corners, especially where function is coming or loading is coming. This is a boss design. Same thing. Ribs, everything is same. Only design, no, it's a down, that is a flat, that's all. So this is thickness. I'm keeping like this. Strength will be lesser. And moreover, here, bottom side, I'll get a sing mark because this thickness is more than this. I can put a big. So what now? This T is there. See, the width, this is maintained like 0.5 to 0.7. If we want a bigger ball, then your part thickness has to go up. There is no other way. You cannot put a 2 mm base thickness or a nominal thickness. You want a screw of 20 M20. It's not possible. For M20, you have to design the part like that. Base thickness also has to go up. Then boss also we can design as per that. Normally for amorphous plastic, very important. Amorphous easily crack. So you have to maintain internal dia 2 and outer 2D. For semi-crystalline nylon PP and all, little you can use 1.5 also. It may not give a problem. So we see W we have seen 0.5 to 0.7 T. Same thing, 0.6 or something you can maintain. This is how we have to design the product design. These are some right and wrong thing. Everybody same thing what we have shown earlier. Just in a single side and see now it is connected, so there is a chance for sigma coming here. So we are given extended and given a gasset. Here see there is wall thickness is thickness is increasing in this area, not uniform. So but application calls for that. Then what we'll do, we'll put a like a hole, scoop out it, remove some, so that it maintains the uniform thing. Okay, here that sharp corners we remove the radius. Sometimes we want a sharpness here, then we somehow remove, scoop out and remove metal from here. It is like this. And see, there is a huge wall thickness change happening here. Gradually we are doing it. We have kept it same. Here also, see, there is a huge wall thickness here. So sigma, blowholes, everything can come. And higher injection, higher holding time, loss in our holding time, cycle time, raw material wastage, our process wastage, everything, weight of the part will go up. Transit loss will be higher. Since weight is higher, our product cost, transport cost, everything goes up. Everything is related. And the quality of the part also, internal blowholes also will be. So let us give some scope out. Maybe little bit increase in the tool cost, but product cost. We should not see the one-time cost. Okay, many people only first tool cost has to be lesser. Part cost, what? Because somebody else is paying. No. see, tool cost can go up, but recurring cost, wherever recurring cost come, no, again, very short my cost is going. If it is a 1 paisa, we should not waste that, because in 6 months we can make a new tool with that cost. So we have to take it. Raw material wastage, sometimes raw material scarcity will be there. You are wasting, no, instead of 2 gram, we are using 5 gram, putting a thicker area. So here we can see, I want this type of holes. So here wall thickness I am not able to maintain uniform. What in this construction design change, what we have done is uniform wall thickness also maintained. Same time we have reduced the, these holes are given for reducing the weight of the part. Suppose awesome, it has been redesigned at this manner so that it reduces the weight also and uniform wall thickness and better filling, easy molding, everything is possible. Here also, no, there is no ribs, no, it is totally unsupported. So if we give some, see, this is a loading element, rotation element. So this can crack, okay, over a period of, these are the given gaskets, proper gaskets. Instead of just increasing the diameter, we increase the diameter also, we get the same purpose, but increase the diameter we call for blowholes, molding issues, no, over wastage of raw material. So this is the optimum design. Like this, multiple cases will come across to us. These are a few cases. This is what we were discussing earlier. We were little bit stuck last time. We're telling up to what thickness is my length of the part is this, and how much thickness I go for that. Which raw material has to be used. I have given an example for this here. I had taken polycarbonate as an example here. First polygon Lexan 101 resin. Okay, this material have a lower flow. It means it can go up to a certain length only. And next material is having a next material have a next flow, means this is very viscous. This material is compared, suppose this 101 is a 6 mfi, next I have a 10 mfi, 1 2 3 I have a 17 mfi, and upper one has a 25 mfi. So 25 mfi one can fill 5 mm 5.5 mm part, and the part length can go up to 1200 mm comfortably. I can fill. If you see the same, the part we are going to use 101 material Lexan, then it can only fill up to 500 mm of part length of the part. 945 can go up to little bit, no, 650, 700.
Do we have similar graphs for other grades also?
It will be available. We have to check with the raw material supplier.
Okay.
If you have confusion on which grade has to use, my part length is 1000 mm. I want to use PC. Which PC? You have to narrow down. No, thickness is 4 mm. Which PC? Better fit. And you have to consult with the raw material people. First, you can narrow down using the MFI. But still go deep, you have to take the data from the raw material manufacturer. You will have the data. Okay?
Yeah.
This is a specimen and this is the result. This is how we can understand this material at what thickness, how much length it can be done. This is very, very informative for product designers. When thread comes means what should be the W value. So Bharti asked that question, very important question. When thread comes mean what is the value? See, thread comes or not, this W value if you increase based on mechanical property, then your sigma mark is going to come. It has to be as per the thickness of the part. If you want to go for a thread, then first of all increase the T, then increase your thread area, whatever it is. So it is like that. And for threading application, always go for a crystalline plastic, not an amorphous. Don't give a self-tapping thread in a polycarbonate or polyester, it cracks. That's why whenever we see a thread, no, it will be semi-crystalline material, maximum case. Otherwise, you have to over-design that product. Thickness, just to provide a thread, we have to increase the thickness by anything to give in amorphous, because amorphous crack. We are telling, no, internal in-molded stress is more for amorphous. Amorphous cannot be expanded. PP, nylon, PBT, all these things, if you put thread, it expands. It will never crack. Because its shape is like bundle, no? We remember it's a bundle. It has a space to expand. Which material can meet what amount of tolerance at what length? If my part is 20 mm, at that, how much tolerance is it possible with this material? If my part is 800 or 500 mm, how much? 1000 mm, how much? This is what here we are telling. In this here in this first chart, we have taken unfilled PC and ABS, which is having a almost similar, both are amorphous, similar shrinkage factor. So there are three type of tolerance in any product design. One is the precision tolerance. Precision means so much critically you are giving a dimension, very difficult to meet in production. Sometimes it will be over defining the product. In a product, the critical product like MCB or very aerospace, some application where a movement is, there will be one or two precision dimension, and second will be reduced one. We are giving a higher tolerance. Okay, little bit better to machine it, maintain it in the tool also to repeatability. We'll get a better stability in the molding also. Third is a nominal tolerance. So whenever I recommend product designer to give nominal tolerance wherever possible, and if it really calls for sometimes we may have given precision tolerance, and when the parts come out, we may not have able to achieve that, but we assemble it, see the performance. It may process in the process is not capable of meeting precision, and we got it is coming in the normal tolerance, and we are doing an operation trial or testing or performance evaluation, and it is working quite okay, then means the normal tolerance is sufficient. We have to change the design, product design, and document it, and change it to normal tolerance. So precise tolerance, try to avoid as far as possible. If cannot avoid, go for a reduced one. Otherwise, go a normal tolerance, which is applicable based on property of the raw material. See, normal tolerance is we will get a wide processing range, rejection rate will be lesser, all these things, and cost of tool making also drastically reduced. To maintain a normal, suppose my dimension is plus or minus 0.2. If I'm making it using a sparking, within one or two pass I can do that. If it is 0.02, I have to go for 3 or 4 times time the machining, and machining time will go up 10 times, not even 2 or 3 times. If I'm using 0.1 tolerance and reducing to 0.5, machining time will not reduce only half. I may be reducing tolerance by half. Machining time will increase by 5 times. Okay. So much slowly we have to do the machining. Unnecessarily, to make our drawing easily, don't give a tight tolerance, because it will impact our cost of the mold, and deviation can come anytime. Product rejection will be high, and our molding setting also very, very critical. We will not get any window to operate. So all these are connected. So huge connection. Throughout the lifetime, people have to struggle with that tolerance. So relax, give generous tolerance wherever is possible. And this is for PC ABS. See this chart. I'll share this video with you. You can just see PC. See 1 mm, below 1 mm, and between 3 mm. Normal is 0.15. I can achieve 0.15 tolerance. If you so much precise, very, very rare case, we can go to 0.5. Okay, this is what. If 800 mm, my part length to 1000 mm, I cannot meet 0. I've seen many drawings. 10 mm also same tolerance, 50 mm also tolerance, 1000 mm same tolerance given. How it is possible? Shrinkage is total length. It's a lengthier part. We cannot control in the same. Even in the machine, CNC machine, if your bigger bed size cannot have so much precision. So it is not possible. So based on this also we have to consider the product design application. This is PCABS. You will get a better tolerance. Amorphous. Okay. Now we go to next material. I take an example. Now this is a crystalline material. Now you see same last condition 1 to 3 mm. Okay. Lower side is almost same, but precision tolerance it cannot meet 0.5. And if we go at a length is keep on increasing. This has a warpage property, very difficult to control the warpage and shrinkage. 800 to 1000 mm, this material normal tolerance is 4.4. Earlier one we amorphous we could get it in 2.9. Huge difference, almost 1.2, 1.3 difference. Difference is 1000 mm. So raw material is a very, very important contributor. The more it is crystalline. If it's a crystalline, form is still severe. So we have to take care of that. See, precise here it is 1.9. Very, very difficult. Here it is just 1.25. That's how raw material gives difference. Now I explained some amorphous and crystalline, both the family covered. Now we are going to, when we add glass to, because semi-crystalline higher shrinkage, when we are adding glass or we are filling it with some mineral or something, then what happens? Then we will get a better tolerance. You see, 800,000 instead of 4.3 came to 2.9 again. So here you can see when I added some filler, and it reduced the shrinkage or whatever we can say deflection. So you can get a better tolerance. But crystalline material, keep in mind, give better as much as tolerance as far as possible. Otherwise, very difficult to prove. Tool cost may go up. Even it wears out the, after some run, the mold get weared out. Then again problem. So possible in the product design, maximum we have to give as per the requirement.